Anyway, thank you so much for inviting me to give this workshop talk. And I changed my title a little bit. I want to talk about the future of wireless and what it will enable. It's a very exciting time for wireless communication, and I will deviate a little bit from what some of the previous talks have done in terms of painting the future of wireless. I like to think I look young, but I've actually been in the wireless business since the 1980s. And I really do believe this is the most exciting time because we're moving away from the early days of cellular, which was the 1980s, where we were trying to just get our analog cell phones to connect up and have the batteries last for, a couple of minutes with these big heavy phones. To now, where pretty much every device with an on-off switch may have the potential capability to communicate with other devices and also to send that information to the backbone cloud. So what's really evolving in this wave of wireless, and I don't like to think about 5G and 6G because those are really marketing terms from the carriers to kind of sell more equipment and get you to buy a new phone. But really, I think of the evolution of wireless as a continuum. And what's happening right now is a sea change, a pivot where we're going to be enabling far more devices that are far more heterogeneous than anything in the past. And this is going to not only be about the next generation of cellular and Wi-Fi, but enabling things like smart cities where we have ubiquitous sensors that are sensing what's happening in the city and able to respond to it. Again, this requires a lot of connectivity of these low power sensors to the cloud because that's where all the processing is happening. Obviously, self-driving cars are going to require a fair amount of wireless communication with very stringent latency constraints. Wouldn't it be nice if instead of all of us being in these two-dimensional Zoom rooms, we could actually have enhanced reality where we're sitting around in auditorium and it feels a lot more like a real interaction than the Zoom interactions through enhanced reality. I'm a huge enthusiast of how wireless connectivity is going to change healthcare, where we have medical devices inside and around our bodies that are monitoring us, that are determining if something's going terribly wrong, and also preventing us from having to go to the hospital. We're already seeing that through, standard doctor visits now are done over the internet as opposed to in person. And one of the other things that I want to emphasize here, and it was brought up in, I think, Wahid's talk, is the notion of ubiquitous communication. We talk about broadband access, we talk about connecting, the billions of people in the world that don't have connectivity, and we've been talking about that for a long time. But in this era of the pandemic, where everything is done via information technology remotely, the digital divide has become so much more apparent, and the inability of the people that aren't connected to even function, to get education, to work, to communicate with loved ones, has the imperative of connecting far more people than we do today. And broadband digital access is much more apparent. And it's not always obvious when we talk about how we're going to develop the future technologies, what that means for ubiquitous communication. Because if you think about things like millimeter wave and terahertz and massive MIMO and even, higher speed PHY layer designs, that's not what's going to get us to ubiquitous communication. And it really, to a large extent, is an economic problem, but it's also a technology problem. How do we get wireless connectivity, not necessarily at super high speeds, across much broader areas? So I'll touch on that a little bit in some of the things I described. Of course, this is a Spectrum workshop. And so I wanted to talk about the fact that we have been in a spectrum deficit for almost a decade now. So if you look at this report, this is from 2013 from the FCC, saying that, as of 2014, we would be 300 megahertz in deficit in the licensed airwaves. to support the exponential growth in data demand. And unfortunately, I haven't found a similar graph like this that's been updated. This is still the best graph to show that, for years now, we have not been able to support the massive growth in demand for wireless data in the licensed band. So then why are we actually able to use our cell phones and wireless devices? Well, it really is because of Wi-Fi. There's 300 megahertz of spectrum in the 5 gig band, and that spectrum is not heavily utilized to the same extent as the licensed spectrum for sure, or even what's in the 2.5 gig band. But now as we move to these much higher data rate requirements, even the Wi-Fi bands are going to start to get filled up, and that's why we're looking at things like millimeter wave and even terahertz. But that spectrum is not a panacea. I'm looking forward to Ted's talk, who is an ultimate optimist and will tell you that we can solve almost everything with millimeter wave and maybe terahertz, but there is still a lot of need for innovation at the lower frequency bands, particularly when we talk about broadband access, because those lower frequency bands have much better coverage at a much lower cost than these high bands. And so if we're thinking about broadband access, we need to be innovating across the entire spectrum, not just looking at the higher bands like millimeter wave and terahertz, where we don't even have good channel models. So there's a lot of research to be done there, but we shouldn't ignore the lower bands, because that's going to be the solution to many of the applications that we need wireless for. I'm just going to throw in, I did a little work on molecular communication, where we're actually using chemicals to send ones and zeros instead of bits. I'm not going to talk about that, but it's kind of it was a fun set of research, but there is a place for molecular potentially. Certainly it doesn't use the licensed spectrum or even the unlicensed spectrum, for things like in-body communication and other specialized techniques. But I'm really going to focus on the use of the wireless spectrum in this talk. The Internet of Things has been on the horizon. It's a little bit like waiting for Godot. So it's been on the horizon for several years now, but we are starting to see an exponential growth in more and more devices being connected over wireless technology. And it's crossing the thing I think that's really interesting about the Internet of Things is two things. One is that it's crossing so many different sectors, from connected cars to connected cities to healthcare, energy systems. And if you say, is the Internet of Things just a buzzword, or is it all hype? Well, there was certainly a lot of hype behind it, but the fact that it is so ubiquitous in so many different sectors and enabling so many new things, new applications in those sectors, means that really there is a push and growth in the Internet of Things that is here to stay, and we need to be able to support that in the wireless networks that we're building up. The other, I think, really interesting thing about the Internet of Things, which was captured in the triangle of the 5G networks, triangle of requirements, is that there are very different requirements across these different sectors than just the next generation of our cell phones. So many of these sectors only need very low rate sensing. Latency is a severe constraint in automated vehicles, for example, that doesn't exist in the same way in phone calls or video calls. I mean, obviously we don't like it when our video freezes, but it doesn't mean that there's a safety issue. And then energy consumption is a huge issue. And I really like the talk earlier about the fact that we've talked about low power energy for a long time, but this is an era where climate change and energy consumption is extremely important and life-threatening to not just people but communities. And when we talk about energy consumption, often we just think about, well, how do we make the batteries of our cell phones last longer? I think we need to think more holistically about the infrastructure and the energy that the infrastructure uses. Even though that isn't running on a battery, it consumes a huge amount of energy worldwide, and will continue to do so. That energy consumption will grow as we move into this next era of growth in 5G and 6G and beyond. So I put this slide up, what's the Internet of Things, because everybody has their own idea behind it. And there's one particular point I want to make. This is the Internet of Things according to Andrea, so you can believe it or not believe it. But to me, it's really taking every device that has an on-off switch and allows those devices to communicate with other electronic devices and to the internet. So of course, we already have many things that are part of the Internet of Things. Everything that we have right now, from our phones to our computers, to our smartwatches, to our cars, and sometimes our refrigerators and appliances, those are already connected to the internet. But what I see going forward is that many, many more devices that were never connected to the internet, like a bottle of water or my tennis shoes, may be connected or will be connected to the internet. And the value of the Internet of Things and the reason that it's growing in all these sectors is not just the communication piece, even though as communication engineers, we often focus on the infrastructure, right? How do we get these things to communicate? The value for much of the Internet of Things is data processing either in the cloud or at the edge in the small cells. And so that's another interesting dimension of the design that we need to think about as wireless system designers is, what is the cloud-based processing or the edge-based processing that's going to take place that's going to make all these or many of these Internet of Things devices capable of doing this large-scale data processing. So data is very ubiquitous in thinking about the future evolution of wireless networks. So again, as I mentioned before, I think that I see the Internet of Things already spanning many, many different sectors. And you could say, well, which is the killer app for the Internet of Things? And I think that we don't know what that is. I like to say, if I knew, I wouldn't tell you. I could do a startup around it, but I have no idea what the killer app is. What we need to do, like Apple did for apps on phones, is build an infrastructure such that whichever applications of the Internet of Things emerge as the most dynamic ones and the biggest ones, we need an infrastructure that's going to be able to support that. And again, I will reiterate that includes thinking about the fact that so much of this data is going into the cloud or into the edge for processing. Okay. So this is the triangle. Again, there's different versions of it where we talk about the promise of 5G, where there's 3 different dimensions from much higher data rates than we have today to ultra reliability for things like automated vehicles to very low energy, 10 years on a battery. And the problem is that it's very difficult to build one network that supports all of these things. And yet we can't have multiple networks because that's just not cost effective. I mean, we do have Wi-Fi and cellular, which are very different networks, but we're not going to build out a whole other set of networks within the cellular license bands, some that do high data rates, some that do low energy, some that do low latency. So I think a real challenge in the design of these future networks is how do we deliver on all of these different edges of this triangle simultaneously with one infrastructure? And I don't think we have a good solution to that. What we've done to a large extent is really build towards the higher data rates. That's what the carriers are selling. You can get 10x higher data rate on your network. Now, fortunately, the way to get to these much higher data rates is small cells, which also gives you better energy consumption because devices are closer to the receiver, so they don't need to transmit as much. The ultra reliability, I think, is just something we haven't solved. It's a very big challenge in wireless because of the laws of physics of wireless propagation and also the cost of building out a wireless infrastructure that's extremely reliable. But I think that we just really haven't gotten to the point of extremely reliable, ultra reliable communication, in part because of technology and in part because of just the challenges of doing that over a wireless network. Okay, so enabling technologies for 5G and beyond. I've been a big proponent of rethinking cellular system design. Even though we've advanced the physical layer tremendously, things like comm, where the base stations are talking to each other, is not something we really invested a lot of thought into. There was work on it during the 3G networks. It didn't work very well. And so we kind of move away from that. I think we need to go back now with all these sophisticated physical layer designs and multiple access designs and these new applications and say, really, from a system level perspective, should we be designing cellular systems differently? Obviously, we need to utilize more spectrum. Although, as I mentioned before, that's not a panacea. It's certainly not a panacea for ubiquitous coverage. Even, large scale coverage for broadband access, but even in a city, it's very difficult due to the laws of physics to get ubiquitous millimeter wave and terahertz, even within a small cell in a large city. We need to do much better at building very low power radios that can operate on a battery for 5 years or 10 years. We don't have anything like that now. Massive MIMO has been a technology that's been around for a long time, a decade at least, and it has shown exceptional promise. I love the idea of using AI to kind of do the beam steering, because we don't necessarily know how to do beam steering in dynamic environments, especially at high frequencies. And in order to do that beam forming well, we need to know the channel, and we don't always know the channel. But one of the other big challenges with this massive MIMO is if you say, okay, that's going to be the way that we solve the propagation challenges of millimeter wave or terahertz. Well, as soon as you get, as soon as you get a shadowing object, that perfect beam breaks apart. And so how do we maintain these pencil thin beams in dynamic environments, particularly when you have shadowing? At these higher frequencies or in channels that are changing very quickly, there's a need for new phi and MAC layer techniques. Multi-hop routing is extremely important, especially again at these high frequencies, because we just don't get very good range at those high frequencies, particularly when our pencil thin massive MIMO beams break apart due to propagation challenges. We also, as I mentioned, we need to think about edge computing and caching, because we can't always take all this massive data that we're sensing and get it up into the cloud. The latency is too big. The complexity of doing centralized optimization is too high. And so that leads to this notion of doing fog-based optimization across the small cells. And I'll talk about that a little bit more. And machine learning, I believe, has a huge role to play. I love the previous talk. I think it has a huge role to play in many different aspects of wireless system design. Now, you could say, well, can't it do everything? Why do we even need engineers? We can just train people in machine learning and it will figure all of this out, and we don't need to do anything. And so, of course, that's a bit tongue in cheek. We've done some work on using machine learning in physical layer design, and that's really to get around the fact that most physical layer design is based on a mathematical channel model. You may not know the model, as we don't know for millimeter wave and terahertz. Even when you know the model, for example, doing equalization in a channel with a lot of memory is a highly complex algorithm. And so if you want these low complexity, low power radios, machine learning can actually enable a lower complexity equalizer than a traditional Viterbi detector. And it does this because there's no need for a channel model or parameters when you're using machine learning. It's learning what to do, doesn't need the underlying mathematical model. It learns it directly from the data. And the solution we found is more robust to estimation error because it's not relying on an accurate channel model. So if you do the machine learning algorithm on a channel that looks a little bit different than the one you were trained on, it turns out that it's very robust. So this is some work that we did in looking at equalization, and we found that obviously the Viterbi algorithm with perfect channel information is great, but as soon as you introduce some errors, Viterbi does much worse than the machine learning algorithm. So of course, machine learning is a bandwagon, and I resisted jumping on because I don't like bandwagon. And so I told my students maybe we should run away and let everybody else who's doing machine learning on the bandwagon do it, and we'll do other real engineering. But it turns out that, in fact, machine learning does play an important role in wireless system design, but we have to approach that with care and figure out where it can have an impact and where it can't. So we found that machine learning can beat theory in the physical layer design of equalizers, particularly channels with large amounts of memory or channels that aren't known perfectly. We've also just recently gotten some results on using machine learning for polar code design when you have a fixed decoder, because polar code design is challenging to figure out which of the channels are frozen versus unfrozen. It may be that machine learning is good at providing approximate solutions to intractable network resource allocation problems. I've been doing resource allocation since my very first academic job back at Caltech in the mid-90s. all of these problems are NP complete or harder than NP complete. And, you know, we haven't really done a great job at doing resource allocation in these NP hard situations. Maybe machine learning has a role to play there. I think it can teach us how to do distributed learning. And this gets back again to the previous talk. The fact that we have wireless networks that are ubiquitous means that we can do distributed learning, distributed machine learning, enabled by wireless networks, and that's very exciting. And then also cross-layer design when we're looking at specific applications. Again, cross-layer design has been an intractable problem. Shannon tells us that source and channel coding should be separate, and there's no loss in optimality, but that's under infinite complexity and latency. So how do we actually design end-to-end networks instead of breaking them into the layers that we do now? And machine learning may have a role to play there. And we've actually done some work on joint source and channel coding for images and for text that show that machine learning can beat traditional techniques. So I already talked a little bit about the millimeter wave massive MIMO. As I said, one of the big challenges there, we can get around the laws of physics using massive MIMO, but the problem is we need to know the channel perfectly in order to form these pencil thin beams. There's also a lot of complexity, which isn't going to work well with low complexity devices. And as soon as we have a shadowing object, that perfect beam goes away. So we've done some work on blind massive MIMO decoding where you don't actually need to know the channel. That's not a machine learning technique. It's basically taking advantage of the mathematics of the optimization and doing a quasi-optimal optimization to figure out how to decode the received symbols. I talked a little bit about rethinking cellular system design. It's interesting that when you look at these pictures, traditional designs going all the way back to the paper by D.H. Ring in the 1940s is that the system is interference limited, and that's why we reuse channels. Now we reuse them every cell. We used to reuse them less frequently. The capacity of a cellular network is unknown because we don't know the capacity of an interference channel. The only upper bound we have on it is assuming that all of the base stations are cooperating with everybody else, then it becomes just a single cell broadcast channel or multiple access channel. And that's obviously way too complex to do in practice. And that was some of the challenges that the 3G systems that we're doing comp ran into. So it's no longer the case that cellular systems are interference limited because we have things like multiple antennas to steer beams away from interfering with receivers. We have multi-user detection. We have cooperating base stations that mean that cells are no longer interfering with each other. And that raises just the interesting question of what is a cell? And that's what I mean by rethinking cellular system design. So how should cellular systems be designed? And should we focus only on capacity? Should we look at coverage? Certainly if we're looking at broadband access or energy consumption or latency constraints, what should be the design metric as we think about redesigning these systems? So small cells are absolutely the solution to increasing cellular system capacity. This has been known for a long time. We did some analysis on it back in the 90s. It's also true from simulations and also true just from field results. But we're going to have hierarchical networks in the distant future because you need to build large cells for coverage and then small cells to fill in the capacity. If you only build small cells, then you have to build out the entire network of small cells before you can service a single phone. So we're always going to have these heterogeneous networks, at least for the next few generations. And this gives an opening to have processing in the cloud to optimize the resources across both the small and the large cells. So we've been doing some work on this optimization, and the problem is that this is an NP hard problem. Even back in second generation systems, when we were looking at resource allocation of frequency channels, that was an NP hard graph coloring problem. Now we have, MIMO, power control, hierarchical networks, so it's NP really hard. But we do have advanced optimization tools that can solve these NP really hard problems. But I think one area that we haven't really investigated sufficiently is going from fully centralized optimization, which is optimal if you don't worry about latency or communication constraints, to fully distributed optimization, which gives you suboptimal performance, and what's in between, which is fog optimization. And of course, I won't talk about it, but there's also the challenge of optimized caching and edge-based computing. So what we've shown is that the x-axis shows forming clusters of neighborhoods. So one neighborhood is fully centralized, 10 neighborhoods on the left and 20 on the right is fully decentralized. And we've shown that there's a 10x loss when you do joint decoding going from fully centralized to fully distributed. There's a 55% loss when you're doing single user decoding. But you see that actually having a small number of neighborhoods can actually give you almost as much gain as fully centralized optimization. So this leads to thinking about this kind of design for other types of wireless networks, and maybe even a very generic software-defined network architecture where you have this unified control plane where you're doing all the optimization in the cloud, matching up applications to the networks that they should run on. And the Shangri-La of that is that you just have a bunch of distributed antennas at different frequencies where this middle layer is matching up the applications to the frequency bands and networks they should run on. And this is really critical for coupled networks where you have very hard constraints on things like latency and energy consumption. Okay, so 6G and beyond, I think is really the way I view it is allowing all people and organizations to interact in the digital world. I see this as ubiquitous, and we're not going to run out of interesting research challenges to solve. So I'm going to wrap up with that. I'll just leave this slide up and give the next few minutes for questions.